With the first session. Our first talk is Data Structure, Abstraction and Incorrectness Separation Logic by Andreas. So take it away.
Yeah, it's not showing again. Oh, no, yeah. Yeah, exactly. So I'm going to talk about data structure abstraction and incorrectness separation logic. And it might be good to know that this is a work in progress based on a mostly complete rock mechanization. And the plan is as follows. So I'll do a quick recap of what I mean by data structure abstraction in a familiar setting, so separation logic. And then we will try to do basically the same thing in incorrectness separation logic and conclude that it doesn't work very well. And then there will be a suggestion how to make it work less bad. Yeah, okay, so let's start with the first item. So by data structure abstraction, I simply mean something like this. So in the pre, we have some predicate connecting up, well, in this example, it's lists. So connecting up heap lists with metalogic lists. And then we have some metalogic function here, cons over metalogic lists. And then we want to connect the stuff that's happening at the program level to the metalogic level. And this is exactly what this triple is doing, right? So it's saying that the behavior of the heap list is contained in the behavior of the metalogic list. So just standard this far. And why is this useful? Well, because we can use these specs later. So when we reason about client code, it could look something like this. So we start with an empty heap, and then we allocate the list, and then we get the empty metalogic list, and then we can add something, and we just update the metalogic list. So the point here being that we don't need to care about what is happening in the heap, we only manipulate our nice metalogic list. So for example, if we would have some code like this afterwards, we would know which branch we would look into without having to look into the heap. We only need to care about the metalogic level. Okay, so that's all fine in verification and separation logic. So what happens in bug finding? So basically we want to do the same thing here. So we have the same program and the aim is, well, we should do the same thing. But of course with like behavioral containment flipped. So now we want all the specified behavior to be actual behavior. So let's throw away our approximate triples and replace them with unapproximate triples. So for this to work, we need, in some sense, separation logic-like specs in incorrectness separation logic. So, for example, for this step, we could do this in separation logic because we had this spec before. So to do the same step, we need, well, essentially the same spec, but in ISL. And this indeed works because basically there's not a lot of abstraction going on here. We have a list in the heap, and we have a list at the metalogic level. So sure, there is abstraction, but there's not a big gap between them. So incorrectness separation logic is not completely useless for abstraction, but if we if we increase the gap between the heap and the metalogic level, then things will break. So let's do that. So let's replace our list with a set. So now we are instead exposing our heap list as a set. So now the gap is bigger. So all of this will be completely fine in verification and separation logic because we would just replace this list cons with this type of insertion into a list, and this will be fine. This is an over-approximate valid spec. But to do this reasoning in incorrectness separation logic, we need this spec. And unfortunately, this spec is not valid. And what is the reason for this? Well, the problem is basically that we have no control over where this new element is inserted into our set. So there are multiple models of this post condition, and we don't know where this V will end up. It can be in the beginning, in the middle, or end, and the actual implementation will add it in. For example, the beginning, the middle, or in the end, or whatever, it doesn't matter because it will not reach all of these. So we have a triple where the full post is not reachable, so this is not valid. So what can we do about this? So you first need to figure out what went wrong. So if you look at the standard definition of the ISL triple, it looks something like this. And the problematic part is really this quantification here. So we have a very strong reachability property here. So we are saying that for all logical environments, theta, and stores and heaps of the post, they are reachable. Yes, here. Yeah, so we can execute to all the models from a model of the pre. So in some sense, this is a reachability guarantee at implementation level because all the heaps are reachable, but when we reason at the level of the abstraction of the spec, we don't really care about the heap. So this is, in some sense, too strong. So I have a suggestion here that if we can weaken this reachability guarantee in the following way, then we will get the specs that we want to be valid to actually be valid. So it would be nice if we could somehow partition the state space with respect to the abstraction of the spec, and then just say that each partition is instead reachable, in some sense saying that the heap is not as important as is encoded in ISL. So after 500 attempts of capturing this formally, this is my current suggestion. And this differs from ISL, or I have highlighted how this differs from ISL with these gray boxes. So specifically, we have relaxed the reachability guarantee of the heap. So instead of saying that all the models of our post is reachable, we have this new existential quantification here, saying that there is some other heap that is actually reachable. So we replace this actual model of the post with an existentially quantified heap. And what constraints do we put on this heap then? So it needs to be a model of the same post and with the same logical environment and store. And it also needs to be frame compatible in the sense that it's compatible with all the frames that are compatible with all the models of the post. So you can think of this as a frame compatible representative. And less formally, we can look at an example and see how this works out in practice. So if we go back to our set example, the partitions would look something like this. So this is the full state space, this full space of the post, or in this case, just the predicate. So the partitions here would be, for example, all the sets that start at others 1 and containing nothing, all the sets